Welcome back to ECE 320A. We are in Unit 2. This is our second video, and that means we're focusing on active filters, which is Chapter 15. You have a homework assignment due at the end of this unit, and our final exam, we're getting close to the end, will be at the end of Unit number 12. In this video, what I want to do is talk briefly about the benefits of using active filters. And when you see active, you might just be thinking, oh, we have some powered device that is helping us create these filters. And in this class, those powered devices will be op amps. So if you're thinking or if you're talking about active filters, you might simply be thinking about op amps, and then we will go ahead and analyze an op amp or an active filter circuit and see what kind of frequency response or Bode plot that particular circuit has for its transfer function, and we'll then be able to become a little bit more comfortable with analyzing active circuits. To start with, why are we interested in active filters? Well, for one, they don't require inductors, and inductors can be heavy and expensive, and if you're trying to build some low frequency filtering devices, that might require, in a passive environment, pretty heavy or large inductor values or large capacitor values, and so it's a little bit more convenient to implement those with active devices. The active devices also provide us an ability to amplify the signal. The passive devices, not so much, unless we have some kind of ringing in there, and so it's not as easy to control the amplification with a passive device. Active devices, it's easier, and we don't have to worry so much about loads on the output side of our circuit when we're dealing with active circuits. We can put some buffers between the inputs and the outputs, and then we don't have to worry about, oh, we just attached a load and that just changed our frequency behavior, or that shifted a pole, or that moved our frequency response around and I didn't expect that. Well, with active filters, we don't have to worry so much about the bandwidth changing when we apply the load, and that's partly because we probably will have some kind of buffering between the filtering circuit and the inputs and outputs of our physical system. So let's look at a particular circuit, and this one is actually coming to us out of the textbook. It's from a particular problem, and it's problem in part C of problem 33 in chapter 15, and in the edition, the newest edition, that's on page 597 of the textbook. We have a couple of capacitors. We have 3 resistors. I've put a lot of different lines on this, but hopefully those will help us understand or guide the discussion when I'm talking about currents flowing in particular directions or in particular wires of this circuit. We obviously have our op amp, but what's not shown is the power supplies that obviously have to be connected to that op amp in order to energize it to make it function the way that we want it to function. And we're assuming that this is an ideal op amp, which means we don't have any current going into the input terminals, either the inverting or non-inverting. And if it's now connected in this negative feedback configuration, which it is, we have this R sub 3, this resistor R sub 3 is actually connecting the output signal back to the inverting terminal of our op amp. That provides us with negative feedback, and that now tries to force this voltage between the inverting and the non-inverting terminals of our op amp to 0, and so we effectively have this virtual short between the inverting and non-inverting inputs in terms of voltage drop. Now let's try to analyze this circuit. And I'm trying to make it clear that I'm now going to be performing Kirchhoff's current law, or KCL, at node 1, which is in red, and at node N, which N is because of the negative input terminal, or the inverting terminal, of our op-amp. So we'll apply KCL at those two node locations. Let's go ahead and start by performing KCL at node number 1. And to do that, we really just see that we have 4 leads coming into node 1. Let's go ahead and say, let's set all of the, or sum the currents exiting node 1, set that sum equal to 0. We have I sub 1 horizontally going left. We have I sub 2 vertically coming down through R sub 2. We have I sub 4 going to the right horizontally through the capacitor, and we have I sub 5 going up through the second capacitor in a vertical direction. If we now identify those particular currents, I sub 1, now I'm labeling V sub 1, the voltage dropped across R sub 2, and that's now the voltage at node 1. V1 minus V sub I, that's the voltage dropped from right to left across R sub 1. And so we divide that voltage drop by R1 to obtain I sub 1. I sub 2 is now the current going down through R sub 2. That's just V1 over R2. I sub 4. Now what we have is we have V sub 1 minus the voltage at node N, which I could just say is V sub N. That's this particular voltage. But look at what that voltage actually corresponds to. In an ideal op-amp configuration, we don't have any voltage dropped across the inverting and non-inverting terminals, and so V sub N is actually connected to ground, and so V sub N really is 0, and the current I sub 4 flowing from left to right horizontally through that capacitor, or the virtual current going through that, is now V1 divided by the impedance of that capacitor, which is 1 over SC. And we then have the implied current going up, I sub 5, is now V1 minus that same V sub N. That's the voltage dropped across the vertical capacitor, but again, V sub N is 0, so we have V sub 1 divided by the impedance of that capacitor, and we're assuming these capacitors are equal, so again we're dividing by 1 over SC for its impedance. We can now clean this up a little bit. Let's go ahead and combine the terms associated with V sub 1. We have 1 over R1, we have 1 over R sub 2, and we have SC coming upstairs in both, or in the third term and the fourth term in this expression. Those all now multiply V sub 1, and the only remaining term is this minus V sub I over R1 that's on the left. If we add that to both sides, then we end up with V sub I over R1 on the right. Doing a little bit more algebra, let's go ahead and put what's in the square bracket over a common denominator, which is now R sub 1, R sub 2. Then we have 1 over R sub 1 will just be R sub 2 plus 1 over R sub 2 can be found by taking R1 over R1, R2. And finally, we have 2 of these SCs, but those now need to be scaled by what we just put in the denominator. So we have 2 R1, R2. Let me go ahead and squeeze. Well, that's okay. Let me go ahead and put the S at the tail, And now we have the square bracketed term written a little bit maybe more cleanly. This r sub 1 is common on the left and the right. We can get rid of that. And we want to know what's v sub 1 in terms of v sub I. So let's now find v sub 1, or just now divide by that expression in square brackets, and we now have r sub 2 over r1 plus r sub 2 plus 2 r1 r2 cs, and that's now times v sub I. So I basically was solving for v sub 1, so let me put that over here. I left v sub 1 on the left. I don't know why I put a subscript I on that. V sub 1 is now equal to, if we just multiply by the reciprocal of this black bracketed expression that scales v sub 1, we now have a transfer function between v sub I and v sub 1. Now we know this transfer function between v sub I and v sub 1. But we really want to know what's happening out here, and so now we need another way or another equation to make that connection, and we can make that connection if we start doing KCL relative to this second node, which I've labeled the N node. So now let's do KCL at node N, and we can now see that, oh, let's go ahead and we have effectively 3 currents going into that node. We're neglecting the current going into the inverting terminal of the op-amp, which we know is 0. So now we have 3 currents to worry about going in. Let's go ahead and set the sum of those 3 currents equal to 0. We have I sub 3 coming from right to left through R sub 3. We have I sub 4 horizontally through that capacitor. And we have I sub 5 vertically through the second capacitor. So making those connections and writing I sub 3 as the voltage drop V sub 0 minus V sub n over R sub 3. I sub 4 is V sub 1 minus V sub n over the impedance of that capacitor, which is 1 over SC. And I sub 5 is V sub 1 minus V sub n, again over that vertical capacitor's impedance, which is 1 over SC. That's what we've now done here, but we also know that because of the negative feedback, there's no voltage drop across the inverting and non-inverting terminals of our op-amp, and the non-inverting terminal is set to ground, so that means the inverting terminal is effectively grounded, and that was what we were labeling as V sub n. That now becomes 0, and we can start to clean this up a little bit. Now we have one equation in terms of the 2 variables of interest, V sub 1 and V sub 0. So that V sub 0 now is equal to, let's go ahead and multiply everything by R sub 3, both sides. That isolates V sub 0 and move everything else on the other side. We have SC going up in the numerator of the middle term and the third term, and we've multiplied everything by R sub 3, and moving the second and third terms to the right introduces a minus sign, so we now have minus R sub 3 times 2 SC V sub 1. Or this is now minus 2 R sub 3 C times S. That will now allow us to connect the input V sub I to the output V sub 0, because we can replace V sub 1 here with this expression for v sub 1. So that now if we do that, this r sub 2 in the numerator will also see this product in the numerator, or that term will now join that other term in the product, so that we now have v sub 0 of s is equal to minus 2, there's the r sub 2 from the earlier transfer function, r sub 3c times s over the denominator of that first transfer function, which is now right here, r1 plus r2 plus 2 times r1 r2c times s. So that we now have r1 plus r sub 2 plus 2 r sub 1 r sub 2c times s. And that is now our transfer function between our input voltage V sub I and the output voltage V sub 0 of that active circuit. Suppose we go ahead and just introduce some particular parameter values for the R's and the C. Suppose we make them all equal to 1. That helps reduce some of the coefficient workload in this case. Now the R2, R3C product collapses. That's just 1. So upstairs we have minus 2s in the transfer function between V sub I and V sub 0. Downstairs we have a 1 plus 1, so there's a 2, plus a 2 times R1, R2C. Again, that product collapses. They're all 1s, so that's plus 2s. And now we have a transfer function for specific parameter values. Realistically, maybe these aren't very reasonable, but let's go ahead and just use those values so that we can understand what kind of a filter we now have in front of us for this active circuit. We can cancel the 2's. We had all 2's in every term, so now we have this transfer function minus s over s plus 1, and this you should start to feel warm and fuzzy about because you know how to really see the magnet or the Bode plot associated with that particular combination of poles and zeros. We have a 0 at the origin, because if we set the numerator equal to 0, that is true when s is equal to 0. So there's our 0 at the origin. And now where is our pole? Well, the pole, we simply have to set the denominator equal to 0. We just have one denominator factor. It's linear in s. So we have s to the 1 plus something, and that plus something is actually our pole. So now we have a pole at minus 1, and that gives us now our transfer function h of s is minus s over s plus 1. Let's just go ahead as a sort of a review, go ahead and sketch what that looks like. And if we sketch the magnitude, we don't have to worry about that minus sign in the magnitude response. We have a 0 at the origin, which now says, oh, it's always sloping. It's upstairs, so we have a positive slope, and it's going up at 20 dB per decade. So let's now see. There is the component of our Bode plot that's due to the 0 at the origin. We also have a pole at 1, and that's going to be flat until we reach omega equal to 1, and then it will start rolling off at 20 dB per decade. So here is our pole component. Here is our zero component. It's going up at plus 20 dB per decade after omega equal to 1. And this, maybe I should have gone ahead and labeled the slope of the 0 down below omega equal to 1, but now if we start combining or adding those pieces together, we have 0 added to this, so this is where we are at until we have both terms active, and they are essentially, one's going up plus 20 dB, the other's going down, so they cancel each other out, and we're now flat beyond omega equal to 1. So this is now the total magnitude response, and it's coming up from the bottom at plus 20 dB per decade. And from this magnitude shape, you should be able to now say what kind of a filter type we're looking at. It's now a high-pass filter. Let's look at the phase plot of this particular transfer function. Now we do need to address that negative sign. That negative sign now is something on the left-hand side of our S-plane. So if we looked at that in the S-plane, now we have, let's say, -1 over here. What's the phase of that? Well, we actually need to go all the way from, and the angles are always measured from this positive real position on the in the complex plane. So a -1 now has an angle of -180 degrees. Contrast that with the 0. The 0 now is this j omega, so the 0 is producing something that's up here, and so that has an angle of 90 degrees. Maybe I should have done that in a different color. Let me go ahead and do that in a different color. So now in green, that's now our 0, and that's the plus 90. So the 0 at the origin is giving us this component in our phase plot. Here is our 0 at the origin. We have -180 degrees due to the negative sign. So here is our angle associated with the constant, and our constant is now -1, which we could also write as 1 at an angle of -180. We want to use -180 just so if we're talking about delays, that introduces a delay in our response. We could have called that a +180, but I like to just think of things as being delayed, so now I introduce a -180 instead of a +180 to get us to this -1. And finally, we have to account for our pole at 1, its phase, and again, the phase of these linear factors is changing across a 2-decade expanse. This is happening, this particular pole breaks at 1, which is 10 to the 0, and at that break, it's right in the middle of where it's transitioning between. It has, for low frequencies, an angle of 0. For high frequencies, it has an angle of -90 since it's a pole, and it now has this linear, the way that we do the straight line approximation of our signals. That's now what we have for this particular transfer function's components. We have a 0 at the origin, we have a pole at 1, and we have a constant of -1. Let's now add all of those up. We have 90 plus 0 minus 180, so that those algebraically combine to give us -90, and they're flat until we start seeing a slope change, and that slope change is due to the pole at 1. Now we're going down until we reach a decade beyond that pole's break frequency, which in this case a decade beyond 1 is 10, and now at the high frequencies we should have plus 90 and minus 90. Those cancel and we have minus 180. So this is now our phase plot associated with this active filter that we began with, and this active filter is now producing a frequency response consistent with a high pass filter. So that now hopefully you have a way of understanding these active filters. We know how to analyze those. We just did some KCL equations at particular nodes. Once we found with parameter values a specific transfer function, we could now identify poles and zeros. And once we know poles and zeros, we can start breaking those down into their component pieces in a Bode plot, and that now allows us to, on the back of a napkin, actually sketch these frequency response shapes.